All right. Hello, YouTube. I think we're live. We'll know in a minute if we're live. Hello, everybody. I see people saying hi. Yeah, hey, we're live. So they've cut the delay down to, it used to take over a minute to see the stream, and now it shows up in a couple of seconds here. So, how are you, Ben, my friend? You're on low bandwidth.
I'm on sucky Wi-Fi right now. It's awful.
So, we've got a lot to show today.
You can hear me okay, though. Like, my audio has no delay, right? I'm just
no delay on the audio. It sounds a little quiet, but that might just be me. I'll ask everybody if they can hear Ben okay. But say something, Ben.
Something.
Did you do that on purpose? You dropped out just
what
now.
What are we looking at? No, I didn't.
Okay, they say you sound fine, Mike says.
Sucky incident.
Yeah. So here's what it is. When you move around a lot, your audio goes to heck.
Oh. So the compression algorithm that Skype's using right now is
aggressive. Let's call it that. Yeah.
Choosing movement over sound or something.
Yeah, yep. So, hey, so we got a bunch of things today. And I'll tell everybody in advance, I've got several things going in my personal life where I may have to suddenly mute the microphone and grab the telephone. So if I suddenly mute, that's what's going on today. But I wanted to start by showing the Autorouter and Proteus, which is kind of how Ben and I first met in the first place. Was Ben, you did a hack chat for Hackaday about routing or auto routers in general. Which was it?
Yeah, it was about auto routers in general, and you kind of jumped on and sort of co-hosted it, I think.
Actually, I missed it. Yeah, so
That's
we
right.
had to be introduced by Sophie later.
That's right. That's what happened. So Sophie, I'd met at the Open Hardware Summit when I was promoting Circuit Maker, and she said, hey, would you do a hack chat? I'm like, all exposure is good, so yes. And then we scheduled it, and then I ran it, and it had some pretty interesting people showed up. Even Paul Stoffridge did. I'm sorry, Paul, if you watch this and I don't pronounce your last name properly. If I do, please get in touch with me and tell me how to say it properly. Paul is a genius, by the way. And when I saw that he was in my hack chat, I'm like, oh, I'm nervous and also like really elated that someone like that would show up. So,
Cool.
And he's super nice guy too. Yeah.
Very
Paul,
cool.
for those who don't know, Paul is the genius behind the Teensy. For his own business reasons, and fair enough, he never released the board design as open source. But the Teensy is a marvelous little set of boards. There's been several generations now. I actually followed a project. I had a Cricket Mini. I'm going way off topic here.
Yeah, no, go for it.
The Cricket Mini, which they were selling at Costco like hotcakes back in the day, dirt cheap. And now I know why, because it was a loss leader, like inkjet printers were a loss leader for ink for quite a long time. Now the ink's still expensive and the printers are really expensive. But the Cricket Mini is a little device, and I'd found online people had managed to use Cricket, and in the early version of it, the software was open enough that they'd made it possible. Someone had written some scripts that could turn the Gerber file of a solder mask, a solder paste stencil layer from a PCB design into a Cricut plan, and you could load it into the Cricut software and cut polyimide film and make your own solder paste stencils for squeegeeing solder paste on, doing your prototyping from a Cricut. So I went to Costco, got the Cricut, and I also was like, well, this is cool for the kids. Like, they'll be able to make custom gift cards and birthday cards for each other and stuff. It'll be fun. Well, it sat in a box in my shed literally for 5 years, and then I pulled it out. By the time I got it out and hooked it up, I discovered that the company that makes the Cricut had basically bricked all of these things and made it so you had to buy an ongoing monthly subscription to their software for the machine to be useful. But the machine I had, the Cricut Mini, was old enough that it was no longer even supported. So it was literally a brick from brand new, just because I left it for 5 years.
Left it sit.
And I got so mad. I'm like, look, I get that if you want to use software and the software is valuable and is productive and is useful to you in your job and has ongoing development and therefore development costs, then paying some sort of maintenance or being on a subscription is fair enough. I have a subscription to the Adobe suite for video editing. To me, it's great value for money. I work for a company that's moved entirely to a subscription model. I couldn't.
But it's not hardware that you bought that's useless. It's software.
Right.
Software subscription's different than hardware.
And it's a two-sided coin. It also means you can buy credits and only pay for it when you're using it, and then the rest of the time, if you're doing 5 boards a year in Fusion, and they take 1 week each, you technically can pay for 5 weeks of subscription if you wanted to. Of course, a whole year subscription is so dirt cheap, and there's other things in the software anyway, like mechanical modeling. So to me, it's easy choice to just get a year subscription. But for different people, like, you have that flexibility. But when it's hardware and they deliberately basically make that decision to brick hardware that you've paid for, like, think about the environmental impact of that as well, just for a second. Like, planned obsolescence in material is bad for the environment. So I just got so mad. So I found someone had actually used a teensy 3.1 microcontroller board and written the code to modify the controller board inside the Cricut Mini to take generic G-code files, and you can generate those from Inkscape or anything, or Fusion.
Right.
And so, of course, I had a couple of teensy boards from an Osh Park party I'd been at, where Osh Park had actually given away some teensy boards that were Osh Park edition. They were the purple solder mask.
Right. We had Hackaday versions of them too. Yeah.
Yeah. So one more thing. Once the office is set up, I'll actually have the Cricut Mini here, and I'll walk through what I did, because the person that wrote the software for it left some reasonable instructions, but not a step-by-step walkthrough. There were enough instructions I was able to get it working, and I was very, very grateful for that effort. But Paul, so this, just to connect this whole thread, Paul Stoffridgen turned up to my hack chat about Autorouters, which we're talking about today. Paul gave away, his whole thing started with an 8051 ROM monitor that he made available for free. And then he developed the Teensy board, and the Teensy is super popular for makers. It's just really powerful because it's I like the Teensy. Free scale. They became based on a Freescale ARM Cortex M4, so you can even do audio DSP on them. They have enough power. They don't have a lot of money, but and then there's more recent versions that have, I think now, the Cortex M7 microcontroller that Freescale just released recently. Well, actually, it's NXP now, isn't it? Freescale got bought. So I'm rambling on and on about Paul and Autorouters and that. And then after that, Sophie said, hey, you really should talk to Bill Hurd.
Right, because I asked about you in vice versa. So, yeah.
And I'm like, oh, I'm totally down to meet the legend that was the chief hardware designer for the 128, of course. Bring it. And then we just hit it off since then. So a little bit of history about the Coriolis effect and how we ended up doing this together.
So, yeah, Mike Fikes replied that an alternative to the Cricket is the Silhouette. I think my wife has one of those. Forget, you just want to use hardware to cut stuff. So, yeah. Somebody asked about the show Halt and Catch Fire in the chat channel, and I'll jump on that one, and that is I never watched it because, first off, the Halt and Catch Fire command is actually a 6502 command. It's an undocumented command, and we came up with that terminology in the 80s, in the mid-80s, like 85. So it's kind of our terminology, and I'm pretty sure that Compaq doesn't really have a Halt and Catch Fire. That's what the Halt Catch Fire show is based on, and so I haven't seen the show, kind of because I was there in real life in a different company. But I haven't watched what Hollywood's done to it. But I wrote the book as if somebody wants to make a real Hollywood thing about something that really did happen, the book was written like, here's your starting material, you know. So,
well, another one I've been meaning to watch and still have not gotten to was actually about Compaq. That was interesting to me because I ended up working for that company in the 90s.
Yeah, I remember you saying.
But it was about these. It was called Digital Cowboys, I think, was the documentary. But I still haven't seen it. I wonder if anyone else on the chat has seen it and if they recommend or if they think it's not accurate. That would be interesting. Right. So what are we looking at here, though? We're
going to look at a couple things today. So I'm going to show the Autorouter from Proteus. But then I drug out one of the C128 boards that Johan Grip did, and I stuck it on the TDR, and I also stuck it on my 1 gigahertz scope being driven by the TDR, and I'm looking at two address lines. And so we're going to start to home in on what happened 35, 40 years ago. And so today we just got some interesting things to show. So one thing I'll say about TDRs is I'm using a CSA 803. And I just saw where Ari Leshansky, I'm mispronouncing his name, just got one and posted a quick video on his of it. So it's a wonderful device. They cost about $500 on eBay, and then the TD SD24 head costs about another $500. But we're going to take a look at it here in a little bit. So, but I wanted to start with the Autorouter. And you and me have experience in another company where the Autorouter kind of always leaves about a third for you to clean up. Would you say that's a fair assumption, fair statement?
Yeah, well, out of the box. But here's the thing. So there's two kinds of people in this world: those who understand binary and those who don't. No, that's not really what I was going to say. There's PCB designers who will never touch an Autorouter and say terrible things like
right. I always hand route each and every trace. Yeah,
the results. Yeah, and or it takes too long to set it up to get the results that I could just do it myself quicker, which is arguable. I think you can argue for and against that. But I think that's a matter of experience. If you decide to use autorouters, then you learn how to dial them in and you develop your own
class-based routing and rules. Stuff. Yeah.
You figure out, okay, these are how I configure my design rules ahead of time to get the result I want. And every good EDA tool, like in Fusion and Eagle, you can save a DRU file, so you can set up a default set. You can do default DRU files that include all your design rules and different layer stacks. So if you know you're going to be trying to do something on a 4-layer board, you can pick your template 4-layer board. I'm sure you can do it in Proteus. I know you can do it in Altium and others too. This concept of templating everything. So once you know what you're doing, you can dial things in and have it preset pretty much. I know a guy And so then there's PCB designers who treat it like personal artwork, and it has to look good, or
Right.
they don't like it. And because autorouters don't care about how it looks, they care about it's connected, and it's connected according to rules.
Right. Which, if you have
So-
good rules, it should look good. It shouldn't look random. It should look like it gave preference to horizontal channels and to different types of because otherwise you'll chew up the board and you'll bind the board to where you can't manually route it later.
Well, that depends. That's also about like
How
know,
good
at least
how good you start.
Half of getting the results is your parts placement too. Like this is why we have air wires, and you can visually place the parts around the board to make sure, like you can actually see if it's going to have an easy time or not based on your air wires or rat's nest.
Rat's
And,
nest, yeah.
Yeah, and so parts placement is a big part of it too. So that's
Right.
That's your board unrouted. It looks like you've got a reasonable amount of room there. Is that a 4-layer board?
This is so I'm not showing power and ground here, which this did route as a 2-layer board with power and ground. So I'm not really showing that today because I tore it all out. But generally what I would do is I would route the power and ground, and the power, of course, means 2 or 3 voltages these days. 1.8 and a 3.3 and then a 5 volt if you're doing 5 volt tolerant. So I just did this as just a quick slapdash example without power and ground. And so I'm going to go ahead and just kick it on while we're talking here. So I'm just going to, so this is using just the defaults, no real no real customization here. So you can't see the default screen that just came up. It's got about 6 different settings, but the main thing is it's going to make 5 routing passes and 5 fan-out passes, and I'm going to tell it to begin routing now. So, and we'll just keep talking, but this should finish here in a couple of minutes, which is, to me, just amazing that it does do an FPGA board in less than, because I've used other packages that get less done and take more time.
Right. It all depends on their, where they got the algorithms from and how they.
Right. This does a good job of changing layers. If I had to comment on it, what I saw with some other auto routers, they really just stick to a layer and the cost, and that's a variable that you can change. But I've gone in there and changed the, hey, go ahead, switch layers, go ahead, drop vias up to like 5 or something. Again, another programmable thing. And yet the Proteus auto router, it changes layers easier than any of the other routers I've seen out of the box.
But so they favor. So that's what you're talking about is path cost.
Yeah.
So,
and
so
it's done already, by the way. So it's already done with 3 missing traces. But you were saying about path cost.
Well, so everything has a path cost and vias. So if you have to go from here to here, and to get there, you're going to have to change layers 2 or 3 times to avoid obstacles. Each time you change layers, each time you put in a via in the path, that has a certain path cost. And then going around something and making the trace, like trace segments have a certain path cost, right?
Right.
So if you have to add more segments, but not place a via, how does the algorithm choose which to use? It's all about path costs.
Right.
So there's a base go no go, like you can't get through this object. There's a conflict, and so there's conflict resolution algorithms in there. But there's also every way of getting something to completion is accumulation of path costs, and it'll try a number of different combinations and pick the one that has the lowest cost. But you can choose, as the user of this, you can change what the path costs are for different types of objects. So if you don't like vias, if you're doing high-speed interconnects and each time you change layers, you're interrupting the impedance and you want to remove that, or for example, PCI bus, and no one even uses PCI now pretty much except some industrial applications. But the PCI bus, the original parallel PCI bus, not PCIe, but before that,
Right,
when
right.
computers were still 32-bit.
The big old parallel thing. Yeah.
Yeah, and there was the 33 megahertz, then the 66, then the 100, and then 133 megahertz parallel PCI buses that were in motherboards from the 90s and early 2000s. Okay, so the PCI specification for if you were designing a PCI card as a peripheral card, PCI specification for motherboards and for the cards allowed no more than 2 vias on a PCI signal.
Right, right. I seem to remember that. Yeah.
So if you were going to try and use an autorouter for those, you had to set up your design rules, and path costs for vias would be considered high in those scenarios.
Right.
But some autorouters don't let you go in and change the path costs. I remember when I was at Altium, for example, Citus, you had a slider for more or less vias. That was all you got. Everything else was about design rules and the order in which you process things. And the path costs were configured in a .ini text file with a big warning comment at the top saying, do not change these unless you're an Altium developer or somebody who really knows what you're doing.
Right, right.
Because Jason Hinston, who implemented that Citus, that they'd acquired it from some company, and then they re-implemented it in Protel. And the guy that did that, who I worked for a time, he spent a lot of time dialing those things in and getting them to where the results were acceptable. And it took a lot of work and time. So,
right,
yeah, anyway.
Right. And there's subtle things too, like, well, if you're on the horizontal plane and you start to go vertical, there has to be a cost with, like, wait a minute, if I start going vertical on the horizontal plane, there's a cost associated with that because now I'm starting to block other horizontal paths. So it has to be good enough to go, well, that's worth the cost of a via, or I'm just going to bind up the whole design, right around the chip. You could bind up a chip with just 2 or 3 traces that go vertical on you when you're trying to go horizontal and vice versa.
So it all comes down to graph theory. This is what we're doing. We're solving a puzzle using well-known computer engineering techniques, plus what used to be considered voodoo magic and secret sauce in EDA space back 20 years ago, but it isn't really now. All the scientific papers you can find in IEEE Explore, and most of these algorithms are pretty well known. Some still have patents that haven't expired, but a lot have. So this is why even cheap PCB design tools now, and for some time, have had at least shape-based auto-routing, because all the original Cooper and Chan shape-based algorithms that were patented, all the patents expired. Cooper and Chan, by the way, was the company that pioneered shape-based auto-routing and had very, very expensive software that they sold with Cadence and Mentor and even Protel back in the day. You could buy this router called Spectra, but then Cadence acquired Spectra, so that was a competitive flanking activity right there, because other companies were bundling Spectra with their own product and being resellers for it. And Cadence said, no, we'll take that and we'll lock everyone else out from having it. What's really funny was they discovered I heard a rumor at least, even some of the chip designers had started using Spectra, which was made for PCB layout auto routing, for laying out place and route, or they would place their standard cells in the silicon, and they would use Spectra. They would do some file conversions to bring it into Spectra at a different scale, and have Spectra auto route it, and then convert back to get it into the chip design tools again. And Cadence really didn't like that, because Spectra even though it was $60,000 or $80,000 a license, it was the darn sight cheaper than the place and route tools for the chip design flow that they had. So,
right.
it's kind of funny how all that sort of goes. But
every good shop has that guy that does those scripts too, that does converge from the tools to the tools, and actually uses all those parts management and everything. You need one guy that's one person that's what they do, is run around and keep everybody else fed and happy. Unfortunately.
Yep, and this is why EDA companies charge a ton of money for their licensing. Usually, PCB design tools don't. Not in my sort of world. But they all use flex licensing and all of this. So companies, they actually have dedicated employees who know how to drive scripting and all of that to check out licenses and automate the whole process. So they're monitoring everything, and they're only paying for what they use as much as possible, and not paying for things that they don't use.
So somebody asked the question I was going to ask, which is, have we seen any progress in AI-based routers that aren't quite so rule driven, but figure out, don't bind up the chip, don't bind up the channel,
Yeah, well, the router you're showing there, which is, I believe, going back to the original shape-based, works so well. The Citus router that Altium has, and the router that we have in Fusion, is AI-based. They have been for some time. The problem with Citus was that they did not have a big enough training set. So it was started by this one company, NeuroRoute, which was the one that Citus came from and Altium acquired back when it was still Protel, nearly 30 years ago, I guess, or 20 years ago, something like that. I still have a user manual for it. But NeuroRoute was the first AI auto router, and the way it worked was the guy that wrote NeuroRoute got a whole lot of PCB designs that were of different layer stacks, different sizes and shapes, and each one, there were 50 of them from what I recall reading. There were 50 different PCB designs, and they were handed to the algorithm before they were routed, and then they were routed by different people to completion and handed to the algorithm after they were routed, and that was the training of the algorithm to develop path costs and all of that stuff. And so it was the first, it did two things differently. It wasn't rectilinear, so it didn't do everything at 90s and 45s, at 90 degree, and it didn't do everything vertical, horizontal, like shape-based routers always would divide the board up into rectangles, and every trace would follow the edges of rectangles. Instead of meshing the board that way, it meshed it into polygons or triangles, much more like finite element method tools do today. It meshed the whole board into triangles, and then it would follow a path across midpoints of triangle sides. And so it could go basically at any angles, and then it would clean up afterwards and go and neaten things up.
Groom it out.
Right. And so that was called topological auto routing, and it was AI based. So it's actually been that way for a long time. But the problem was to train AI, you need a very large data set, and 50 boards, even if they're complex.
That doesn't sound very big to me.
And that's as much as they could do back then, because think about it, the computing power. When NeuroRoute was released as a product, the Pentium had only just hit the market. So people were still using 486s, 386s, and the Pentium was brand new and super expensive, and in the workstations at the time, they didn't have much memory, they didn't have much CPU power compared to what we have now. So AI, it was a good idea, but people have known how to do it since the 50s with Marvin Minsky set up the AI lab at MIT. He's the father of the whole thing, Marvin Minsky. Read up on him if you haven't.
Okay.
But so the theories were there, but the computing power to support it wasn't, and the pool of designs to work from. So my thinking is, what we need to do for autorouters and for current generation EDA, we should be actually gathering data anonymously. We don't want to give away people's IP, right? But we ought to, if people agree to opt in to use a certain tool, we ought to set up a distributed, decentralized AI
learning
on
base,
the cloud,
yeah.
internet. So everyone who's using that PCB routing software as their routing boards and doing things and getting to completion, it's actually taking every board design and analyzing it and analyzing what the users did to feed the AI training globally. So over time, it just keeps getting better and better over time. And eventually, more and more people will start using the router. And it will do more and more human-looking results. So it's a good,
you described shape-based routers a little bit here. So what are the general routers? And you said shape-based tries to do things based on squares and the perimeter of squares. In general, what are the different kind of auto routers other than AI, which we've talked about also?
Well, it's really just two that I'm familiar with. There's shape-based and which is also called rectilinear, and there's topological, which most like we have in Fusion. We use a topological router. It's super fast. There's a few companies that specifically make topological routing technology in the world. Rectilinear is sort of the old school, but it's pretty reliable and usually does a very good job. And that's your Cooper and Chan sort of style algorithms that were in Spectra, and what we can see here in Proteus. If you've got room and you've placed your components well, it's pretty fast. And so a lot of people still use that just because it's convenient. I was just going to say also that, I know other PCB design engineers who often use autorouters, and they don't care what it looks like because it works, and because it allows them, in the same time it would take them to do one to do the board completely once, they could do it overnight with maybe 8 or 10 different part placement and different iterations, then the next day go through and review each one and pick the one that is best.
Right. Now, I've used Autorouter two major ways. One is as a tool to tell me how routable is this, where I'll give it a shot and I go, oh, look, there's some natural channels that are forming. Or look, I got 80% done. Hey, the placement is doable mostly. And then the other, when I was doing Hackaday videos once a month, where it takes me through, I would need to do a PC board in just a day or two. I'd throw it in the Autorouter and laugh all the way to the, throw it in the Autorouter, throw it at one of the PCB houses, get it back in a week, and then it's going in the trash right after the video's done, and so it worked well enough. And and I was using Proteus for that. I went through several versions of PC boards where I did almost no cleanup. I was just throwing it in the mine is power and ground. I always do power and ground myself,
Yeah. Now, of course, there's situations where you're never going to be able to use that. So, like anything analog or RF, you're probably not going to,
No. Right.
It'll route it, but it's assuming autorouters always come from this assumption that you're doing digital electronics.
Yeah.
And
yeah. And parts placement is
what I haven't seen them do yet. Maybe some of the higher end expensive tools do this, but I haven't seen it do any high speed stuff like length tuning. I think Topper can do that. The Topper router can auto route, but then also on top of that go and do length tuning and all of that stuff for high speed.
Right. So Kevin asked in the chat group about can trace length mess with timing, and that's too big a topic to discuss here today. But I'll throw it out real quick that yes, absolutely. And there's two different forms of it. One is just what does a single trace do? But then when we talk about length tuning, a lot of times we're talking about pairs of routes or groups of traces, so that we get it's not how long it took, it's that it took the same amount of time for members of a logical function, whether it's a differential pair or SDRAM DQ lines or something.
DDR. If you're routing to a DDR chip, you have to length match. Particularly DDR2 was the most stringent on this, where it required a lot of effort on the PCB design side. DDR3, they started doing tuning. Some degree of tuning is done on chip, and DDR4 took that even a step further. So it started getting easier, but you still want to do length tuning on the board. And the software can do it. You know, almost every ECAD tool can do at least basic length tuning now. So you might as well do it if you've got the space.
Right. Now, are you saying the DDR4 can handle bigger alterations between signal lines in the chip, that it can learn the signal lines individually as opposed to as a group of lines?
Yeah, to an extent, but you've got to remember that
to like 10% or something like that.
Yeah, there's not much room on the silicon, so it's not gonna do crazy magic tricks for you, but but it does make the board layout easier, because this signal propagation on the silicon is because it's on silicon, right? And it's oxide substrates. The propagation delays for the same lengths are different than they are on a printed circuit board.
Would they use techniques like delay lock lines, or would they not go that far for individual DDR4 signals?
I don't know. I think that's the intellectual property of Micron and others, but
all right. I'll have to look into that, what they're actually doing.
I think they do similar things to what I found in the Lattice FPGAs that they talk about, where they actually have programmable delay lines on die, where it's like a multi-tap sort of, or it's a mux with,
Right. And again, there's limited fidelity in silicon, because silicon's just so dang fast normally.
Right.
So, all right. So that's a good summary of.
Talking about delay. What are we seeing there on the DDR?
So let's talk about the DDR. A matter of fact, I'll go to the big one here. There's a big shot of the TDR. I'm sorry, geez. And so what I've done is on these Commodore 128 boards from 35, 40 years ago.
The CSA 803s are not $500, by the way. They're way more expensive than that because of our show, probably.
Well, that's how much I paid for mine. I paid $500 for that and $500 for the TDR head. But so we've got these 35-year-old boards, and one of the traces on here, and Johan corrected me. He said it's A3, not A10, and he's absolutely correct. On the motherboard, there's a wire that I added specifically to thwart a problem. And so I started looking at, well, what does that jumper do? And it starts by looking and say, well, what are we up against here? And I threw it on the TDR first. And at first it looks, smoking gun, there it is. And I'll talk about that in a second. But what I did right after that was I threw another address line right on. Mike Fikes just said he got his CSA for $250. I put on another address line. It's a matter of watching eBay long enough, or like you said, we might have driven the price up on it, right?
You and Mike and Alan Walkie are driving up secondhand instrument costs.
Yeah. Trust me, for the first time in a long time, I was looking at actually LCR meters. What I want is an LCR meter that gives me a good ESR reading for like electrolytic caps that you could really say, no, that's a low ESR cap that's broken. You know, not something that fudges the impedance because it can't tell X sub C from the effective series resistance. So maybe that's for next week, is to talk about LCR meters, because I think you and Mike had the same LCR meter.
Oh, yeah. Yeah, I got the handheld one, and then you'd posted that the signal path video on the high end
where it goes ESR 0.50 milli 50 milliohms. I'm like, yeah, that's what I want. It's something that just tells me outright how good a cap it is, or whether it's broken or not. So what I did, though, was I took one of these boards and I carefully soldered a pigtail on it for SMA, and I compared two address lines. And if we look at the printout here, the very first thing you'll notice here is I've calibrated it in inches per division. And you can't see my cursor, but down in the middle, matter of fact, right here, you can see it's set for 1.6 inches per division. Wow, why'd the camera move? That was weird.
Yep.
And then the other thing that I didn't know my CSA could do, but Mike Fikes clued me in on, is that I can read out impedance, but I have to use the cursors. So you set the readout to read in row, RHO, and then the cursor function will read out in impedance. So let me see if I can do that real quick. And if I can't, I'm not going to try. So hang on. Hey, there we go. So you can see that my impedance around the cursor, and the cursor is the little red dot. If you look at the bottom one, you'll see I threw it just in the center of this gobbledygook. For the first 7 to a dozen inches of this board, it's about 116 ohms. All right,
that's pretty high.
Which is nowhere near 50 ohms. But I'll tell you that an LS gate output, which is what was driving, or an NMOS output, is nowhere near 50 ohms either.
Right, yeah,
so,
it didn't matter back then. And we used reflections actually we didn't know it, but we were actually using reflections in our favor to a degree.
Or we just waited for them to settle out.
Ground plane.
Yeah, we didn't have ground plane. So let's be real clear. The reason this isn't 50 ohms is there's no ground in this thing except around the edge and a little tiny one that shoots across the board. This is a random pile of wires for all practical purposes, and it comes out to be about 95 to 100 ohms by the time a wire makes it from here to here. Now, the address line 3 that is an issue did take a different path, and so I thought, aha, is it the fact it went up to what we call the data river, and we've talked about that before, and then drops down, versus coming straight across? And the answer is, well, no. When I put on A2, which does go straight across, it looks real similar. You do see the slight hump on the red trace, but, you know, you can stare at this too much and try and draw too many conclusions. And this isn't a terminated. All I'm doing is looking at the first dozen inches of propagation. This isn't terminated. These reflections will bounce back and forth until they die a slow, meaningless death, you know, without actual parts in there to catch it. So, but what's interesting is there is this hump, and so I threw it on my Tektronix scope, which has a gig, and I said, oh, look at that, there's overshoot. And I wanted to know how much overshoot, so I go to my measurement. Let me see if I can do this real quick. And I see that I have a, now it's saying 60% overshoot. That's not right. But it was reading 25% earlier, which, so I wanted to show this, that these days scopes can do a lot of the calculation for you with the rise time. So what we did was we went from an almost immeasurable rise time to a 5 nanosecond rise time just by putting it on the PC board, just the inductance of the board and the capacitance of there. And it makes the signal pretty ugly. There is that overshoot. Let me get rid of the this screen here. Hang on. And so what I did here was I said, oh, look, there is overshoot. When I measure it, this is 1 volt. This is the signal coming out of the TDR. So it's not a logic level. It's not 5 volts. It's about 1 volt. And so this little 1/10 of an inch, almost 0.2 inch volts, I mean, turns out to be about 20% overshoot. And in real life, during this time when it's overshooting and then undershooting, if this was a clock, it'd be in an illegal state till it settles down, especially the overshoot part.
Right.
So,
and this
so what
is
that's
also
saying,
why logic came out being edge triggered.
yes. And so what that's saying is that for the day, we would do a series resistor to do impedance matching on a clock, but address lines, they set up so early, we just threw away the 10 or 20 nanoseconds waiting. You know, a microsecond, we had a microsecond to wait for stuff to settle out. Not really, but it was a long time. You know, a microsecond's 1,000 nanoseconds. And so we calculated in our boards, we threw away 5 nanoseconds just on the capacitance of the board when I did my timing diagrams. Well, it turns out, look how close I was. I'm at 5.5 nanoseconds. So it was pretty close. So, but I'm measuring this. What's interesting about the way I'm measuring this is there's no room in here for a scope ground lead of 2 or 3 inches. That would throw this measurement way off. This is being sampled again, you know, at a gigahertz. And I wanted to show what I'd used for a ground.
You have to, and that's a whole other subject. We don't have time now today, but we should get into this soon. Is de-embedding.
Yes. Yeah.
How to eliminate all the surroundings and the probes themselves and the probe cables to measurement instrument. How to cut those out of what you're looking at to look at just the device under test.
Right. So you can see here.
The embedding.
Yeah. Right. Don't you flip it to the click? I call it click and strip, but it's something stripping for de-embedding. You transfer to the T domain or something. So for ground, you'll notice there is no big ground lead. Here. Normally a ground lead looks like that. That's way too long for this measurement. So what I've got is, yeah, the ground clip is this little collar, and it just sits on the tip of the, and you can't even see them because they're behind the probes.
Did you make that, or did it come with the probe?
I have a box of these with the probe, but I soldered to them. They're spring steel, but they're solderable. So I couldn't get the spring steel to sit exactly like I wanted, so I took a lead off of an MLC capacitor, soldered it to it, and then I can form this a little bit so that when I push down, it makes solid contact. So, and then I just,
even if needed, you can solder it to the ground plane on the board.
If I had to, yeah.
The probe.
Yeah.
If you had a ground plane, yeah.
Right. So I wanted to show this about how serious I was about the grounding on my scope probe. Is I had to use something, the ground, and again, there's a collar on your scope probe, and that's what I'm grounding against. Is if you ever see that little metal thing, that's not just there, that's actually the ground for when you're doing low impedance pickups like this for grounding.
Those are also designed so that you can have coaxial connectors for test points on your board. So you can actually design the board to use a test collar that is a socket that's for the scope pin, and a collar around it that's grounded, soldered into your ground plane, and the scope probe plugs right into it like a coax connector.
Right. And I looked at trying to see if I could solder a collar to the board, and I just ended up using the wire method. So now here's the thing. I've got a piece of wire here. I'm going to simulate adding the wire to the board. Now again, this board's not being used in real life. It doesn't have chips hanging off it. It doesn't have distributed terminations like LS devices would be, and it's being driven from 50 ohms. But still, it's like, well, what was the wire doing for me, given that I was living with some kind of reflection? And the answer is going to be that the difference between A3 and A2, for example, we're going to find out that it was the signal that was different, not the routing. In other words, if I took that same signal and put it on A2, it'd probably have problems also. But watch what happens when here, let me see if I can. So if I can do this without I don't even have to worry about blowing up the board.
Yeah, because no parts on it, it's not powered up. That's the reason it's good to do measurements on a prototype before you've actually put any components on it.
Yep.
So are you soldering that on right now, Bill, or are you just going to hold it?
No, I'm just touching it, and I'm not seeing the results that I'm expecting. So I have to describe them if they don't show up here in a second. There it goes. See the red wire? The red trace?
Yeah, it's dropping in impedance. You're dropping the
impedance look at the ringing
and bringing
on the yellow
that
trace.
Overshoot down.
Yeah, the ringing went way down. So
yeah, that's really noticeable on that yellow trace.
Yes. So what I was doing was lowering the impedance. You know, if you look back and say, well, what the heck were you doing definitively that said, look, this will work in millions? You know, I didn't want to just move where the reflection was. I wanted to stomp it, but I had limited tools. I couldn't really insert a series resistor because there was multiple drivers. Well, where do you put the series resistor? In front of the 6502? Or in front of the Z80. Well, the problem is the Z80, right? But I didn't want to make a 6502. By adding the wire, what I did was I actually was giving it 2 transmission lines in parallel, and I also gave them where they would come around and form a loop, and you would get the 2 fronts meeting. So there's 2 ways to model it, but ultimately I was lowering the impedance and consequently lowering the ringing. So now I'm going to go ahead, and not today, but I'm going to hook this to a live board and actually watch the effect on a live signal. That's where I'm headed with this. But I'm starting with a blank board, just seeing what the effect was. And the effect's pretty pronounced. I dropped the impedance. Now it drops by 10 ohms, and you'd say, whoa, that's not very much. Well, wait a minute, 10 ohms out of a 95, that's 10% change. That's something.
Yeah, it is. Yeah, and this is why we, even with board manufacturers, we're trying to get within 10% of what we specify.
Right.
Because manufacturing tolerances can, you know, each individual thing, like etch factor, may have a tolerance at a good fab of, you know, realistically 3%. But then you also have board thickness, and that's a tolerance of 3% or whatever. So all of these things multiply and have a more profound effect together, which is why in manufacturing people love to run Monte Carlo simulations, because it's like we want to see random variations based on all of these different things that can vary, plus the extreme values. If everything's at completely the minimum, least material condition, we'd say in PCB fabrication, it's called least material condition, and all the way at the max material condition, and all the extremes around that as well. So you might have the maximum laminated thickness of a dielectric in your PCB with the maximum over etching. So that means the thinnest trace, which is the highest impedance, and the thickest dielectric and the thinnest trace combine to give you the maximum impedance, the highest impedance,
Right.
that might
Right.
go outside your 10% range, right? So, yeah, all of these things are kind of important.
Yeah, somebody said they have a C64 board with a diode and resistor in parallel. Kevin Smith did. I'd have to look at that to see where that's being used. I'll tell you that C64 boards were open game in production. We went through a phase where engineers were not allowed downstairs. We were not allowed to see what was going on. And they were doing things like gluing capacitors on RAS and CAS, which it would make it appear to work, but it was actually making the rise time out of spec and things. So they could have been doing anything by they might have been trying to dampen something down with the diode and resistor. I'd have to see where it is in the board. It might be a power reason too. It depends if it was near the power supply or the cassette or something like that. So, yeah, Joanne Grip says some of the Commodore assembly line fixes can be a bit funky. Oh, some of them work worse than no fix at all. Absolutely. Putting a capacitor on RAS or CAS will cause it, in my experience, to fail every 20 minutes, but it would pass the 2-minute test. But the damn thing wouldn't work for half an hour. And then the caps themselves were such poor quality that you change the temperature on it and it stopped working again. So hey, hang on a second, I got to grab a phone call.
There it is. We're 3 minutes from time, so there was a lot to cover today, and we need to get into that time domain reflectometry a bit more and how to de-embed your signals. I'm supposed to be able to take over while Bill's on the phone, and wouldn't you know it, that's just the moment my head goes blank. But there's a lot. Now, I know I promised everyone to do a tour of my new office and lab here. It's unfortunately, like all of these things, I'm trying to get set up outside of regular working hours, which means I have very limited time. It's coming along. You can see I've got I think I had this last week too, the acoustic wall behind me, which I put up, but the other side where my workbench is, and I'm going to have all my instruments and stuff. So I get to look like one of the big kids like Bill and Alan and these guys. Well, I don't have the ridiculously prized possessions of TDRs yet, but I'm getting there.
We'll have to get you one. Yeah, that's well. If Mike's right, so and they only cost $250. Set a eBay search for it. Now, what I did was I saw somebody advertise a TDR, and I looked them up, and they were a test equipment company, and I approached them outside of eBay, and I made a deal. And by doing that, they pre-tested it, changed out the real-time clock on mine and stuff. So I didn't buy mine from eBay, but I got the name of the vendor from eBay by looking at what they were advertising. So eBay probably doesn't want me telling that story, but
I am seeing some others that are newer versions. Like there's a few TDS 8000 and a CSA 8000. Pretty much
the 1180-803 that's got Ethernet on it. Basically, you could web to it just like I do for my scope.
Yeah, so there are some things out there. I think the real key is that these are mostly mainframes with the UI and the display, and then you have to get the add-ons. You have to get the modules, and that's where it can start getting a bit more expensive, because the real secret sources are special chips and charge coupled devices, ultra high speed advanced electronics in the modules. Right. Yeah, but there are a lot of good used equipment there, and it's just some of it. It's like, are you willing to repair it if it comes back and doesn't turn on, or or got obliterated in shipping? And these things are heavy and big, and that's why I probably will never sell my equipment,
to somebody that can't walk up and drive away with it is I'm not putting this stuff in boxes.
Yeah, some of them are just right. Some of this stuff is pretty crazy heavy.
Right.
And
So
it might be 200 to buy, but another 100 to ship.
Yeah. So, all right, look at the time. We're at the top of the hour here. I do have to jump here to take care of some business offline. Let's just say it's been a busy day. But hey, we had an hour here between us that everything was quiet. So we had a good hour.
Yep. Thanks, Bill. It's been a great show. You showed some really cool stuff today. And hope it was
and somebody asked about
for those that watch.
Yeah, and somebody asked about showing the 80 column chip the way it had an issue on the 128. That's certainly something we can talk about in the future show. I love talking about the old stuff and how frustrating it was to get right, but we got a lot of it working in spite of itself. So Johan's saying he drove 700 kilometers to pick up his microscope. So
there were a
excellent.
lot of factors. Yeah. Cool. Thanks, man. Good
All
to
right,
see you.
Ben.
Thanks,
It's great seeing you. And we'll see you next week. And we'll have some other stuff to show. So everybody have a good weekend. Have a safe weekend.